This is SpaceTime, Series 23, Episode 110. Coming up on SpaceTime. Carbon, one of life's key building blocks, produced faster than thought. The OSIRIS Rex spacecraft about to touch down on the asteroid Bennu. And North Korea's monstrous new missile. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found that stars produce carbon, one of the key building blocks of life as we know it, some 34% faster than previously thought. The findings, reported in the journals Physical Review Letters and Physical Review C, may trigger a major shift in science's understanding of how stars evolve and die, how the elements are created, and even the origins and abundance of carbon across the universe. Stars produce carbon through the triple alpha process, where three alpha particles, that is helium nuclei, collide and fuse together within a tiny fraction of a second. But this process is so unlikely that for many years astrophysicists were at a loss to explain how carbon and heavier elements could be created. Then in 1953, the renowned astronomer Sir Fred Hoyle suggested a solution to the problem through a previously unknown excited state of carbon, very close to the energy of the triple alpha process. This excited state, now known as the Hoyle state, acts as a sort of stepping stone, producing a stable carbon atom, which in turn paves the way for future fusion reactions, allowing stars to make heavier elements from oxygen through to iron and beyond. The carbon and other elements formed inside stars eventually become the dust and gas from which planets and ultimately life are formed. But even with the help of this Hoyle state, the formation of stable carbon is still very unlikely. In fact, for every 2,500 Hoyle state nuclei produced, only one would transform into stable carbon. All the rest fall apart. Existing measurements for the state of carbon production in stars dates back to the 1970s. So physicists at the Australian National University and the University of Oslo decided to reproduce the results using today's more modern and sophisticated technologies. Shockingly, they found that when they reproduced how stars made carbon through the Hoyle state, it was actually being produced 34% faster than previously thought. One of the study's authors, Associate Professor Tibor Kibiti from the Australian National University, says it was a surprising result which will have profound implications across astrophysics. He says, put simply, if the Hoyle state didn't exist, neither would we. Directly measuring the rate of carbon production is very difficult, so instead the authors calculated it indirectly using observations of two different Hoyle state transitions. To measure the first transition, Kibiti and colleagues used the ANU's Heavy Ion Accelerator facility to fire a proton beam at an extremely thin sheet of carbon in order to form Hoyle state nuclei. A tiny fraction of the excited nuclei transitioned back into stable carbon by emitting an electron-positron pair, which the team detected with the accelerator's Super E pair spectrometer. The ANU team also worked with researchers at the University of Oslo's synchrotron laboratory in order to measure the second transition, in which the Hoyle state emits a photon. They observed some 6 billion Hoyle state reactions, of which just 200 decayed through photon decay. By combining the ANU and Oslo results, the authors calculated the carbon production rate to be more than a third larger than previously thought. This unexpected result represents a major change for such a critical astrophysical quantity, and it'll have a big impact on models of stellar evolution. It's going to affect science's understanding of how stars change over time, how they produce elements heavier than carbon, how astronomers measure the age of stars, how often we expect to see supernova explosions, and even whether they're going to leave behind neutron stars or black holes. SpaceTime spoke with both Associate Professor Tibor Kibiti and the head of the ANU's Department of Nuclear Physics, Professor Andrew Stutchbury. And we started by asking Professor Stutchbury about the sorts of stars which make carbon.
So the stars that make carbon are called red giant stars. They're much bigger than our sun, and they make it relatively late in their life cycle. After they've used up the hydrogen and they're starting to burn helium. So most stars mainly burn hydrogen, which is the lightest element, and they burn it and convert it into helium. And in the red giant stars, after all the hydrogen has been converted to helium, effectively they can then start to burn the helium and it's at that stage that the carbon will begin to be made. Our sun is a bit too small it will never reach this stage, so it's a bigger kind of star. The universe has been through several stages of stars forming and then exploding, distributing their contents out into space and then reforming. So there's been a development in the way stars form, what they're made of. The later generations are made from the ashes of the earlier generations, and to some degree the red giants are an earlier generation than, for example, our sun.
And an important part of this is the triple alpha process and also the Hoyle state of carbon.
Yeah, let me try to explain. So how carbon is made in a star, it was something which is a puzzle. There are no stable elements, no stepping stone when helium particles can fuse together and form the carbon-12. Barium-8, which is assembled from two alpha particles, it's very short-lived. And if the third alpha particle comes, it will be carbon-12. But physicists realized if that would be a simple process like this one, helium would be used up pretty fast, and too much carbon will be produced, and too little oxygen, which will be the next step when helium is fusing with the carbon, and star would use up all the helium and wouldn't be able to make the oxygen. Fred Hoyle had the brilliant idea there must be a state just above the energy, very close to the energy, when three alpha particles fuse together, and that should be a resonance state. It means that it's unbound, it's not stable, and most of the time it decays back to where it came from, disintegrate. Nothing happened. And 1 out of 2,500 times it will decay down to the ground state, and this is where carbon is made. And everything else heavier than carbon will be based on this.
And everyone sort of accepted this. This looked like it was accurate.
It has been tested, and a lot of measurements were done back in the 1970s. The critical quantity we need to measure is how many times that you form this Hoyle state, this resonance state. It mostly falls apart again, but as Tibor indicated, about once in every 2,500 times, it will decay to the ground state of carbon-12, and that is where all the carbon in the universe comes from. So this is a very important number to know what that fraction is. Is it exactly 1 in 2,500? Is it a little bit more? Is it a little bit less? It's difficult to measure because it's so rare. Most of the time that you form this state in carbon-12, it goes back into three alpha particles. Now, of course, you can't assemble a stellar atmosphere in the laboratory and fuse three helium nuclei together like you do in the star, but you can excite that state in carbon-12 by various nuclear reactions, and a relatively simple one, just by taking some of the carbon that once upon a time was made in a supernova and putting it in your accelerator and hitting it with a proton beam, you can excite it up to the Hoyle state and then see what happens. Most of the time, it will fall apart back into alpha particles, but every now and then, it will decay electromagnetically. And what that means is it will emit two high-energy photons, two gamma rays, and go down to the lowest state of carbon, the ground state, which is the way the carbon in our bodies exists. So, of course, very many measurements were done back in the 70s and earlier to try to measure this process. They're difficult measurements. A number was arrived at, but it wasn't checked.
And that's what your research did.
Yeah, and so what we did was that we went back to check it, and the more that we looked at these old measurements, the more we got uneasy about whether they were actually accurate or not. People were very careful, but it's such a difficult measurement, and between now and the 1970s, detector systems have improved and data acquisition systems have improved. So this advance in technology has allowed us to do a more accurate measurement.
And there were two labs involved in this, the ANU and also Oslo.
Yes. Originally, we wanted to do everything here at the ANU. And that would be the first ever experiment in history when all the transitions which are responsible for carbon production is measured in a single experiment. We had to learn that is not possible. It's just too tough. So we done one part of the experiment at the ENU, one of the transition of the two, which coming from the Holy State, and we went to Oslo to do the second measurement for the second transition. So we practically, from the two measurements, when we combine together, that is our outcome, that the carbon production rate is 34% higher than what we expected before.
I've got to ask you, did you go to Oslo in the Northern Hemisphere, summer or winter?
Winter.
It was winter.
Yes, it was cold.
It was cold, I bet. But it's still beautiful.
Yeah, so we were running for 12 days for that experiment, but they were very kind to us. Yeah.
Tell me about the results you got from these experiments.
When we started this project in around 2007, 2008, the aim was to reduce the uncertainty, the error bar, from 10% to 5%. And what we got now is a 34% change. So it's a huge change compared to the old value. When we compare with the various measurements, there is one particular one which we find very similar to ours. It's a much smaller equipment, but we also find some interesting details about some problems with that experiment. So we believe that it could be a human error. They overlooked. We really don't know what has happened. Other measurements are extremely tough, the way how they done it. And I can understand that easy to make that kind of mistake. So the change, getting a different answer.
So what does that mean for our understanding of carbon production in stars? The rate changes, obviously.
That's a very interesting question. There is a recent article when astrophysicists, they are nuclear physicists, astrophysicists done some very detailed calculations combining all our knowledge and model predictions about nuclear synthesis in stars. Not just carbon and oxygen, but everything else. And from their studies, they established that there is a linear relation between the oxygen and carbon production. These are the two elements absolutely important, but they can't really limit or restrict or establish what would be the rate what we can expect. And they making the conclusion is that if one of the rates will be fixed, then it will restrict the other production rate. So having a new value from our experiments will also restrict the oxygen production rate in the universe. And of course, we would like to see more experiments to verify that our finding is correct.
So I could add that this carbon-12 production is, if you like, it's the doorway to the evolution of the star and how it develops. It's also the doorway for production of all the elements in the universe. So it's important for detailed understanding of how the elements are made and how stars evolve. So there's more complicated nuances that Tibor was talking about. The simple thing is that this is the first step, and the first step is an important step to get right.
Tell me about the Heavy Ion Accelerator facility at ANU. I mean, I normally think of things like the synchrotron down at Monash or, on a more exotic scale, I guess, the Large Hadron Collider. But
the Heavy Ion Accelerator, it accelerates heavy ions, which for us means not electrons. So, for example, the synchrotron accelerates electrons and then makes synchrotron radiation. The Heavy Ion Accelerator can accelerate any element in the periodic table except those that won't form a negative ion. So that's a handful of elements. We can run proton beams. We can run most elements. In fact, we run, for example, plutonium, which is probably the heaviest.
That's pretty heavy, yeah.
Yeah, it's the heaviest thing, and that's actually done for a technique called accelerator mass spectrometry, where we use the whole accelerator as a very sensitive atom counter, and we use that for doing environmental science and other aspects of astrophysics and so on. So the Heavy Ion Accelerator facility is the only experimental facility in Australia that does what you would call true, pure and applied nuclear physics. There are other accelerators that focus on applications of nuclear physics, but we're the only one that does pure research as well as some applied research.
And is it a circular thing or is it a straight line?
No, it's a tower.
It's a tower.
Actually an electrostatic accelerator, and it's in a tower. It's a feature of the Canberra skyline.
That's Professor Andrew Stutchbury and Associate Professor Tibor Kibiti from the Australian National University. And this is SpaceTime. I'm Stuart Gary. Still to come, OSIRIS Rex about to touch down on the asteroid Bennu, and North Korea's monstrous new missile. All that and more still to come on SpaceTime. This episode of SpaceTime is brought to you by LastPass, simplifying your online life. Now, if you're anything like me, one of the biggest frustrations and time-consuming parts of going online anywhere is trying to remember and then use all those login details and passwords that you've built up over the years. And again, like me, you probably already have hundreds of them. Of course, on the other hand, you could just be like a lot of other people out there and simply use one password for everything, and that's not a particularly secure idea. But I guess it could be worse. You could be one of those people that use 1, 2, 3, 4, 5 or A, B, C, D, E, or worst of all, you could use password as your password. And with the internet getting more and more dangerous, now really is the time to do something about that. And the good news is there's a great solution out there. It's called LastPass Password Manager. And with it, suddenly all those security hassles are gone. And believe me, the relief really is unbelievable. Not to mention the time it saves you. And it's so convenient having everything stored in the one manageable dashboard. If you sign up for LastPass, you'll be joining some 25.6 million fellow users around the world and more than 70,000 businesses. Now, you've got to admit, that's a lot of trust with one of the most important aspects of online life. And the good news is all this peace of mind is really affordable. If you want, you can simply sign up for the free service and leave it at that. Or for even more features, get the premium package, which is $4.50 a month. There are family and enterprise plans available as well. Plus, LastPass works across all devices and even suggests super secure passwords for you to use. So, why not put your passwords into autopilot and reduce the stress? You can check out LastPass at spacetimewithstuartgary.com/LastPass. That way, you'll be helping to support our show. So sign up and use it for free at spacetimewithstuartgary.com/LastPass and simplify your life. And like always, you'll find the link details in the show notes and on our website. That's spacetimewithstuartgary.com/LastPass. And now, it's back to the show.
This is SpaceTime with Stuart Gary.
The final countdown is now underway in preparation for NASA's OSIRIS Rex spacecraft to touch down on the surface of the asteroid Bennu to collect samples for eventual return to Earth. In fact, depending on where you are, by the time you hear this program, it might already have happened. This so-called touch and go onto the asteroid's boulder-strewn surface is the climax of the 9-year-long OSIRIS Rex mission. The 492-metre-wide asteroid Bennu is a near-Earth object. It is an orbit which intersects and crosses the Earth's orbit around the Sun. But its orbit is intrinsically dynamically unstable. And that means Bennu is one of the highest known chances of hitting the Earth, with a 1 in 2,700 chance of impacting our planet sometime between 2175 and 2199. If it were to hit the Earth, the resulting impact will be the equivalent of a 1,200 megaton thermonuclear device. Maybe not big enough to destroy an entire planet, but certainly enough to wipe out an entire country. Launched from the Cape Canaveral Air Force Station in Florida aboard an Atlas V rocket on September 8, 2016, the 2,110-kilogram OSIRIS Rex spacecraft arrived at Bennu in October 2018. The probe spending 3 years orbiting the asteroid, mapping its surface and geology, studying its evolution, its composition and structure, looking at its chemistry and its mineralogy. One of the mission's key objectives was understanding non-gravitational influences such as the Joukowsky effect, in which sunlight heats up the surface of the asteroid. That heat's then radiated back into space as the asteroid rotates, providing a small amount of thrust. Knowing Bennu's physical properties will be crucial for scientists trying to determine the likelihood of this mountain-sized asteroid slamming into the Earth. During its upcoming sample collection maneuver, the spacecraft will try and retrieve up to 2 kilograms of pristine asteroid regolith. The first attempt will be made at a target site known as Nightingale, a rocky area about 20 metres wide in Bennu's northern hemisphere. Now, if the attempt's unsuccessful, the spacecraft will try again at a backup site called Osprey. If all goes according to plan, OSIRIS Rex will leave orbit in March 2021, with the sample return capsule being jettisoned for a parachute landing in Utah on September 24, 2023. This report from NASA TV.
A historic moment is on the horizon for NASA's OSIRIS Rex mission. On October 20th, the OSIRIS Rex spacecraft will journey to asteroid Bennu's boulder-strewn surface and briefly touch down to gather a sample. Something NASA has never done before. Right now, OSIRIS Rex preparing for its descent to sample Site Nightingale, a dark crater near Bennu's North Pole. Site Nightingale is one of the only areas on Bennu that holds enough fine-grained material for the spacecraft to safely access. The crater is only 66 feet in diameter, or about the size of a tennis court. The Nightingale site itself is only 26 feet wide, nearly the width of 3 parking spaces. From orbit departure to the steep descent to the backaway burn, the spacecraft will perform the entire sample collection sequence autonomously. To safely touch the site, the spacecraft has to position itself for the touch-and-go sample collection maneuver. OSIRIS Rex will first stretch out its sampling arm from the folded, parked position. Then, it will slowly move its solar panels into the Y-wing configuration, placing the solar panels up and away from the asteroid's surface during touchdown. This configuration also places the spacecraft's center of gravity directly over the TAG-SAM collector head, which is the only part of the spacecraft that will contact Bennu's surface during the sample collection event. As OSIRIS Rex descends to Nightingale, it will approach the site and fly over building-sized boulders scattered around the crater's rim. The tallest one is about the same height as a 3-story building. This spacecraft will spend approximately 22 minutes deeply descending to the rocky surface. While OSIRIS Rex descends, remember, OSIRIS Rex is aiming to tag a spot no larger than a few parking spaces. In between these boulders are small patches of relatively clear surface, enough to allow OSIRIS Rex to collect at least 60 grams of pristine asteroid sample. With just meters to go, OSIRIS Rex is now ready to collect a sample. Once the sample collector head senses contact with Bennu's surface, it will fire a small puff of compressed nitrogen to kick up debris and capture pieces of the asteroid into the collector head, an event that lasts just a few seconds. OSIRIS Rex will then fire its thrusters to slowly back away from the surface and navigate to a safe distance away from Bennu. A couple days later, this spacecraft will image the inside of the sample collector head to verify that material was in fact collected. The sample will be delivered to Earth in September 2023.
Since OSIRIS Rex arrived at Bennu, scientists have been characterizing the asteroid's composition and comparing it to other asteroids and meteorites. 3 new studies reported in the journal Science have been looking at Bennu. They've discovered carbon-bearing compounds on Bennu's surface, a first for any near-Earth asteroid. They've also found minerals containing or formed by water. Scientists studied the distribution of these minerals globally and at the sample sites. One of the study's authors, Vicki Hamilton from the Southwest Research Institute in San Antonio, Texas, says recent studies show that the organics and minerals associated with the presence of water are scattered broadly right around Bennu's surface, so any sample returned to Earth should contain these compounds and minerals. Hamilton and colleagues will compare the sample's relative abundances of organics, carbonates, silicates and other minerals to those found in meteorites in order to help determine the scenarios which best explain Bennu's surface composition. Asteroid Bennu is a dark rubble pile held together by gravity and thought to be the collisional remnant of what was a much larger main belt asteroid. Its rubble pile nature and heavily cratered surface indicates that Bennu's had a rough and tumble life since being liberated from its much larger parent asteroid millions or possibly even billions of years ago. Boulders strewn about the Nightingale site have bright carbonate veins, a compositional trait Bennu shares with aqueously altered meteorites. This correlation suggests that at least some carbonaceous asteroids were altered by percolated water early in their history. The boulders on Bennu have diverse textures and colours. That may provide information about their variable exposure over time to micrometeorite bombardment and the solar wind. Studying colour and reflectance data provides information about the geologic history of planetary surfaces. Bennu's diverse surface includes abundant primitive material potentially from different depths of its parent body, as well as a small proportion of foreign materials from another asteroid family which is littered about its surface. Both the primary and backup sample sites, Nightingale and Osprey, are situated within small, spectrally reddish craters that are thought to be more pristine, having experienced less space weathering than most of Bennu's bluish surface. The OSIRIS Rex team's also been comparing Bennu to Ryugu, another near-Earth asteroid. Both asteroids are thought to have originated from primitive asteroid families within the inner main asteroid belt between Mars and Jupiter. The Japan Aerospace Exploration Agency JAXA launched the Hayabusa 2 mission in 2014, which rendezvoused with Ryugu in 2018. After surveying the asteroid for a year and a half and sending a number of rovers down to the surface, Hayabusa 2 collected a number of samples of Ryugu, which are expected to be returned to Earth, parachuting down into the Woomera rocket range in outback South Australia on December the 6th. The samples returned by OSIRIS Rex, combined with the surface context maps the spacecraft collected, will improve interpretations of available ground and space telescope data for other primitive dark asteroids. Comparing returned Bennu samples with those from Ryugu will be instrumental in understanding the diversity within and the history of asteroid families and the entire main asteroid belt. Meanwhile, a separate study, reported in the journal Science Advances, suggests that Bennu's interior could be much weaker and less dense than its outer layers. The findings by the University of Colorado Boulder's OSIRIS Rex team could give scientists new insights into the evolution of the solar system's asteroids, how bodies like Bennu transform over millions to billions of years. Using OSIRIS Rex's mapping instruments and other tools, scientists spent nearly 2 years mapping the ebbs and flows of Bennu's gravitational field. Measuring the asteroid's gravitational field with enough precision allows scientists to determine regions of differing densities below the surface, effectively showing its internal structure. The data suggests the asteroid's core appears to be much weaker than its exterior, a fact which could ultimately put the asteroid's survival at risk in the not-too-distant future. The thinking is Bennu could simply fly apart as its rotational speed increases. As the name suggests, being a rubble pile asteroid means Bennu's little more than loosely held together mounds of debris. Asteroids also change over time, thanks to things like sunlight affecting how they spin and collisions with other asteroids. By studying how bits of rock were flung from Bennu's surface and then fall back down again, scientists were able to build an extremely detailed gravitational map. Now, as we mentioned on SpaceTime the other week, rocks on Bennu are initially flung up into space through the release of energy as they crack open due to heat stress caused by repeated hot and cold cycles as the asteroid rotates and different parts of the asteroid are exposed to sunlight. The authors combined this rock data with readings from OSIRIS Rex itself as the asteroid tugged on the spacecraft over many months. They discovered something surprising. Before the mission began, scientists had always assumed that Bennu would have a homogeneous interior. After all, a pile of rocks is a pile of rocks. But the gravitational field measurements are suggesting something very different. To explain those patterns, certain chunks of Bennu's interior would likely need to be more tightly packed than others. And some of the least dense spots on the asteroid seem to lie around a distinct bulge at its equator and another right at its core. The asteroid's rotation may be responsible for these voids. Scientists know that Bennu's rate of rotation is increasing, and that building momentum could be slowly pushing material away from the asteroid's centre and towards its surface. What it all means is that Bennu may very well be in the process of spinning itself to pieces. This is SpaceTime. Still to come, North Korea unveils a monstrous new missile, and later in the science report, new studies show the COVID-19 coronavirus can survive for up to 28 days on some common surfaces. All that and more coming up on SpaceTime. The world got a wake-up call this week when North Korea unveiled its monstrous new intercontinental ballistic missile during a military parade in Pyongyang celebrating the dictatorship's 75th anniversary. Experts are still assessing photographs of the giant new ICBM, which was displayed on a modified 11-axle mobile launcher. Now, the mobile launcher is important because it was originally built as one of 8 Chinese WS-51-200 8-axle mobile launchers sold to North Korea by Beijing, allegedly for use as lumber carriers in order to avoid United Nations sanctions. But why the modifications to increase it from 8 to 11 axles? Well, the obvious reason is size. This new missile appears to be an expanded version of the Hwasong-15, which North Korea successfully test-fired in November 2017. Now, assuming it's real and not just a mock-up for show, then this new bigger missile, which analysts have tentatively named the Hwasong-16, looks like it's a liquid-fueled two-stage rocket, both longer and with far greater diameter than the Hwasong 15. Now, we can only go by the photographs, but initial estimates suggest that it's about 25 to 26 metres long and around 2.5 to 2.9 metres in diameter, which makes it around 4 to 4.5 metres longer and around half a metre wider in diameter than the Hwasong 15. And that raises the question of why. See, the Hwasong 15's first stage uses two Soviet Union-era RD-250-based rocket engines. That provides enough thrust to send a 1-ton thermonuclear payload over a range of roughly 13,000 kilometres, and that allows Pyongyang to hit anywhere it wants to in Western Europe or the United States. So, if Pyongyang already has enough range thanks to the Hwasong 15, why the new bigger rocket? Well, the new missile's first stage is large enough to accommodate 4 of those Soviet RD-250-sized rocket engines we spoke about. And that suggests it's designed to increase payload capacity, either because they haven't miniaturized their nuclear warheads enough, and we know that was a problem a few years ago, or alternatively, it's designed to deliver either multiple nuclear warheads or a mixture of nuclear and decoy warheads. But there's yet another issue, and that's the fact that it appears to be liquid-fueled. In some ways, launching a liquid-fueled rocket from a mobile launcher can defeat the purpose of mobile launchers as being available for rapid deployment. That's because the hydrazine rocket propellant used in these missiles is highly volatile and extremely corrosive. So, the missile could only be fueled just prior to its launch. But when we say just prior to launch, it would require half a day and several fuel trucks. And that's not rapid deployment. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study has found that the COVID-19 coronavirus can survive for up to 28 days on some common surfaces. The research by the CSIRO found that the deadly virus survives on a wide range of surfaces, including mobile phone screens and other glass, as well as banknotes and stainless steel, with survival rates longer at lower temperatures. It also tended to survive longer on smooth and non-porous surfaces compared to porous complex surfaces such as cotton. And interestingly, it survived longer on paper banknotes than the polymer notes we use in Australia. The study, reported in the journal Virology, was carried out by the Australian Centre for Disease Preparedness in Geelong, one of 4 biosafety 4 labs in Australia. Establishing how long the virus remains viable on surfaces enables health authorities to more accurately predict and mitigate its spread. So far, some 39 million people have been infected and over 1 million killed by the COVID-19 coronavirus in the 11 months since it first originated in Wuhan, China. A new study claims moderate exercise is just as effective as high-intensity training in order to keep older people healthy. The findings, reported in the British Medical Journal, involved some 1,567 patients over a 5-year period. 400 participants were assigned twice-weekly sessions of high-intensity interval training. Another 387 were given moderate-intensity continuous training, and another 780 were simply asked to follow the Norwegian guidelines for physical activity as part of a control group. At the end of the study period, researchers found death rates were the same in all groups, and they also found no differences in either cardiovascular diseases or cancer rates. Scientists studying fish populations in Australia's Murray-Darling River system have pulled together more than 600 research papers to develop plans to try and save 9 species of fish currently classified as conservation priorities. The findings, reported in the Journal of Marine and Freshwater Research, suggest the biggest known gaps concern the early life stage requirements, survival, growth rates, condition and movements. Key threats include reduced connectivity, altered flow rates in the river systems, a loss of refuges, reductions in both flowing and slackwater riverine habitats, the degradation of wetland habitats, the introduction of alien species, and the loss of aquatic vegetation. A new species of mosasaur has been identified in northern Morocco. The fossilized remains of a metre-long skull and isolated bones were discovered in a local phosphate mine. A report in the Journal of Systematic Paleontology says Gavialimemus almargeribensis has a long, narrow snout with interlocking teeth, similar to some crocodiles, which paleontologists believe help to catch fast-moving prey. More than a dozen types of these dinosaur-age reptiles, some reaching lengths of up to 17 metres, swam in the Cretaceous period marine environment in what is now Morocco between 72 and 66 million years ago. Well, as Halloween draws nearer and the hocus-pocus of the psychic world becomes more powerful, one needs to prepare and defend oneself from the spirits of the other side. And of course, to help you battle the evil to come, you'll need your 4 so-called clairsenses, which every good paranormal practitioner must master if you intend to receive information psychically from the great beyond. Tim Mendham from Australian Skeptics explains, as well as clairvoyance, that's the one we all knew about, there's also claircognition, clairaudience, and clairsentience. And those who really believe in this sort of stuff take it all very seriously.
The clairsenses that you're supposed to have if you're psychic, and perhaps you don't have all of them. One is clairvoyance, which is probably, you see things, visions, etc. That's pretty straightforward. One is clairaudience, you hear things, and, they can be noises, whatever, that you're picking up. Then there's one called claircognition, which is basically, it's described an intense gut feeling, psychic knowing. So there's that one. And the fourth one seems to be much the same thing, which is clairsentience, which is you feel it. So I'm not quite sure whether a gut feeling and a tactile feeling, a tingling in your spine are different things or what, but that's supposedly the 4 clair senses. 4 clairs, yes. So if you can have
Karens, I guess.
Oh dear. Thank you. Yeah, so that's the 4 clairs, and this is an article in a website called Well and Good. That's obviously about food and skincare and that sort of fitness and that sort of stuff, and then they go into the spiritual side and everything like that. This was from someone who basically was having some anxious feelings, and naturally what you do is you pull out a tarot card.
Well, of course, first thing you do, yes.
First thing you do is, which you ask the question, what would make me feel better about myself right now? Well, obviously pulling out a tarot card is probably going to help. And they pulled out the High Priestess, which was divine, all-powerful, intuitive, all this sort of stuff, all the usual sort of words that are used to describe this sort of paranormal well-being and a feel-good sort of thing. And so then she goes into the fact that she probably did this because of her clairsenses. So, like you, I didn't realise there were 4. I knew several of them, but as I said, 2 of them sound like they overlap a bit.
Have any of them ever been scientifically proven?
No.
Oh.
There's been lots of tests. I mean, there were famous tests of Uri Geller done in the US in the 1970s. The Ben Spoon Man, that was a place called Stanford Research Institute, which was not Stanford University, as people like to point out, especially the people from Stanford University. They tested him for his ability to read things, obviously his bending spoon, which is sort of physical psychic powers, but also his ability to be clairvoyant, pick up messages, see things from a distance, that sort of stuff.
And yet he totally missed what happened to his good friend Michael Jackson. Completely missed that.
He actually was very supportive of Theresa May.
Okay.
He said he actually got her the job of Prime Minister of England, for which she must have been very grateful.
Chalice, but wasn't it?
That was, yeah. So he's been tested. James Randi, the famous skeptic, described the people who were testing him as the Laurel and Hardy of the parapsychology world. There's a whole range of different people who have tried to do testings. The problem is getting tests that are well controlled, well set up, that don't allow for any sort of alternative explanations, and really they don't exist. Again, James Randi tested out the same laboratory, same research group by training a couple of young magicians to pretend to be psychics, and they did all the same things that supposed psychics could do, and they went in and these people tested them and they announced that they were the real thing, really good, and then during a press conference they just revealed, no, we're fakes. And naturally the researchers got very upset, not about the fact that they were exposed, that because someone was pulling a trick. The interesting thing about a lot of researchers in this area do not like being exposed.
Funny
they'll often ignore it. Yeah, funny that. A lot of tests done over the years, but no, really there is nothing which is conclusive of any sort of psychic power, because we have our challenge for psychics who can prove what they do. It's $100,000 we'll give them if they can prove their psychic abilities.
Still sitting there, folks.
No one has. Yeah, it's still there. No one has. I mean, they're serious tests. They're tests that both sides agree to. So it's fair and above board. But no one gets past the first hurdle, actually, because they really can't do what they say they can do. Psychics and people often avoid the test these days because they don't like putting it to the test.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.